We have reached the point where a physical piece of silicon can listen to human speech, parse the meaning of those words, and synthesize an audible reply entirely on its own. The specific hardware executing this complete loop is the Raspberry Pi RP2350. It retails for 80 cents. This processor operates within tight physical constraints, possessing less than 500 kilobytes of total active memory. It is a standalone system. The board has no Wi-Fi module, no cellular radio, no connection to cloud servers. Standard voice AI architectures require gigabytes of RAM to hold language models, relying on remote server farms to handle the computational load. Pushing an entire voice agent onto an 80-cent offline chip requires an architecture built around hardware-level memory orchestration. This diagram outlines the starting limits for the Raspberry Pi RP2350, 520 kilobytes of SRAM. Within that boundary, neural computations are capped at 384 kilobytes in the arena. A complete voice pipeline requires 3 heavy neural models to listen, transcribe, and speak. The immediate engineering bottleneck is volume. If the active memory requirements of these 3 models are stacked together, they massively overflow the 384 kilobyte arena. The developers of Moonshine Micro solved this by abandoning parallel processing. They structured the pipeline to execute through strict sequential timesharing. By forcing each neural model to occupy the same memory space in sequence, the system fits a massive pipeline into a tiny footprint. The pipeline begins with the listening phase, driven by the TinyVAD CNN model. To permanently store this specific algorithm, the system consumes about 89 kilobytes of static flash memory. When the device is actively awake and listening, this model drops into the arena. It occupies a small sliver of SRAM, requiring only 36 kilobytes. To understand the efficiency of this rest-in state, we measure the effort in MMACs, millions of multiply accumulates, which tracks the computational cost per cycle. Executing the math to verify human sound costs about 0.8 MMAC per single frame of audio. Scaled out to a continuous monitoring state, the processor sustains a light 25 MMAC per second while waiting for a voice. Because its footprint is small, the voice activity detector acts as an efficient gatekeeper. The heavier models remain dormant until a voice is present. The millisecond the gatekeeper verifies human speech, the transcription stage boots up. This second step relies on the spelling CNN speech-to-text module. The static storage requirement jumps to 1.3 megabytes of flash memory to hold the language model. The system clears the VAD from active memory and allocates 346 kilobytes of SRAM to hold the new transcription state. Notice how 346 kilobytes sits right against the absolute ceiling of the 384 kilobyte arena. Holding this active state and processing the incoming words demands roughly 36 MMAC per second. If the voice detection model remained loaded alongside transcription, the system would instantly suffer an SRAM overflow. Time sharing the memory block prevents the crash. Once the spoken command is transcribed into text, the pipeline moves to the final stage, a neural diphone synthesizer that generates an audio response. The embedded voice pack requires 1.8 megabytes of flash memory. The system clears the transcription module and executes its final RAM swap, allowing the synthesizer to claim 340 kilobytes of the arena. The resulting outgoing voice audio runs at a crisp 16 kilohertz. Pushing out a typical reply establishes a baseline computational load of roughly 37 MMAC. Generating the audio causes the highest compute spike in the pipeline, forcing the processor to peak at 65 MMAC per second. Neural text-to-speech is computationally expensive for embedded hardware. It only functions on a microcontroller by isolating it as the sole active task. The pipeline is a sequence of clearing and loading. First, it actively listens, swaps memory to transcribe, swaps memory to synthesize, and then it speaks. Because of this sequence, the active memory costs are not additive. This data table illustrates how the math works when memory is shared. Across the entire demo, the peak active RAM stays beneath the 468 kilobytes provisioned for the system. Static storage behaves differently. Flash memory is additive, requiring roughly 3.6 megabytes for the combined models. Processing tasks sequentially should theoretically cause a bottleneck, as the hardware has to dump and load models for every interaction. The success of this architecture depends on the end-to-end latency. from the moment a user finishes speaking a command to the second the audio output begins. The delay measures between 0.7 and 1.0 seconds. The hardware lacks the capacity for simultaneous processing. However, through orchestration, it delivers response times that match much larger cloud-connected systems. Isolating complex intelligence onto a standalone microchip changes the way we design consumer hardware. This map visualizes an architecture where data never leaves the silicon. Because the device lacks a network radio, there is no physical path for a voice recording to reach a remote server. Smart speakers typically rely on the promises of a privacy policy. A standalone microcontroller relies on the absence of a transmitter. This makes it possible to add voice interfaces to hyper-cheap appliances, like light switches or medical monitors, where adding Wi-Fi is too expensive. Moving the processing to the local chip entirely removes recurring costs for server maintenance, bandwidth scaling, and remote API queries. The standard industry model mandates server farms to process human speech. Running a functional voice agent locally on an 80-cent piece of silicon removes that requirement.